How do our glasses correct for vision? That's a very good question. One of the things to remember is this is a two-lens problem. We really have two lenses involved here. We have the lens in the eye and the lens of the glasses. So there is some important information that we need to know in order to do these problems. The power of your glasses is measured in diopters, and the power is 1 over our focal length. But we have to remember, and this is hard to make yourself do, but your focal length has to be in meters. So a lot of the problems that we're going to do are in centimeters. You need to, once you get your focal length, make sure you convert it to meters. A positive D is for farsighted people. So if you have glasses or your prescription, it has a positive prescription, like a positive 1.5 or a positive 0.75 even, that means that you're farsighted, which means you can see far, but you can't see close. So you're called farsighted because you can see far. And a negative power, so if you have it like a negative 1.75, that means that you're nearsighted. Okay, that means that you can't, like if you're sitting at the back of the classroom, you can't see the board very easily. So you're nearsighted. You can see things that are close. You don't need your glasses to read things, but to see something that's far away, you need to put your glasses on. So remember how we said that the power is 1 over the focal length? We can actually tell what kind of glasses are being used by the power. Okay? Glasses with a positive focal length are made of convex lenses, because remember, a convex lens has a positive focal point. And if you are farsighted and you can't see things close, if you need glasses to read, if you run your hand down your glasses, you will see that they are thicker in the middle than they are on the outside. People that are nearsighted have a negative focal length, and lenses with a negative focal length are concave. And if you run your fingers along your glasses, you will see that they are thinner in the middle than they are on the outside. Now, normal power. Okay, so the normal power for your eyes depends on where you are standing. Okay, so it's 50 Ds, oops, that's a 50 Ds for far vision, so when your object's at infinity, and it's 54 Ds for near vision, and I'll show you how we get those. Okay, so we need to define a couple points, the near point and the far point. These are defined in your book too. The near point is the closest that you can see comfortably. And the far point is the furthest you can see. Now, in a perfect world, your far point will be infinity. Okay, so if you have perfect vision, your far point is infinity, because you can see the sun, which is at infinity. You can see the stars, which are at infinity. Somebody that is nearsighted and not farsighted has trouble actually seeing the stars. So we have our thin lens equation, which doesn't go away. So it's still 1 over F equals 1 over DI plus 1 over DO. Well, our object at our far point, we're going to do the far point first because that's easier, is infinity. Okay? 1 over infinity is pretty much 0. We just call that 0. It's close enough. Yes, technically it's undefined, but it's 0. So then we have 1 over f equals 1 over di. So where is the image being formed? Here's our eyeball. The image is being formed on the back of your eyeball. So the distance from the lens in your eye to the back of your eyeball is about 2 centimeters. So 1 over f is equal to 1 over 2. So f equals 2 centimeters. So when we go to find the power is 1 over our focal length, but remember we have to change this to meters. So this is 0.02 meters. So our power is 1 over 0.02, which comes out to 50 diopters, or 50D. So that's how we get that normal far vision has a power of 50D. So this is normal far vision. Now the normal near point for people, the closest that normal people can see is 25 centimeters. So we just call that's kind of like the standard near point. Okay, so this would be our object distance. And then our image is still the back of the eyeball. So this is uncorrected. This is without your glasses on. So it's still back of the eyeball. And so 1 over f is equal to 1 over 25 plus 1 over 2. So your focal length comes out to 1.85 centimeters. So our power, change that to meters, 0.0185 meters is 1 over 0.0185, which comes out to 54 diopters. So that's normal close vision. So your glasses need to correct. Okay, if you're farsighted and you have that convex lens, this lens needs to correct to 54 diopters. So glasses is a basic well, it's not real basic, but it's a 2-lens problem. You have your object that you're looking at, okay, and that would be at your near point or your far point. You have your glasses, so that's one lens, and then you have the other lens in your eyes. So remember when we did 2-lens problems, the image from the first lens becomes the object for the second lens. And your glasses need to correct so that the far point is infinity and your near point is 25 centimeters. So these distances will be the object distance. Object distances for the actual glasses, because we want the image to appear at the person's, okay, so the person's actual near point or far point. Because, okay, so let's think about this, okay? These are the normal, this is what's normal, okay? And so I want to be able to view with my eyes, I want to view something at 25 centimeters. But the image formed by these glasses is going to be the object for my eye. The image formed by the glasses is going to be the object for my eye. My eye can only see at my eye's near point and far point. Okay, this is normal. This is where I'm going to put the object. I'm going to put the book right here at 25 centimeters. So my glasses need to make the image be where my near point is, way out over here. So my glasses need to make the near point way out here so that my eye can focus on this. My eye is going to focus on the image from the glasses. That's a little confusing. Which one's the object and which one's the image? But remember, the object or the image from the first set of lenses becomes the object for the second set of lenses. So your eye can only focus at your near point or far point. Okay? Okay, so here we're talking about near point. So the near point, we're going to use the 25 centimeters. If it was far point, we would use infinity. Near point, you're going to use 25. Far point, you're going to use infinity. Okay, she's going to wear contact lenses, so her contact lenses are basically right on her eyes. So this distance here is basically 0, so we don't have to worry about that. When we repeat that with glasses, we'll see how that comes into play. Okay, so her eyeball can only see it if it's out here 60 centimeters away. Okay, so we need the lens, we need the contact lenses when something is held 25 centimeters away to produce an image that is 60 centimeters away, because then her eye can focus on it. Her eye can't focus on anything closer than 60 centimeters. So 1 over f, because we're looking for what power, so we need the focal length. 1 over f equals 1 over 25, that's our DO, plus 1 over, now this is kind of tricky. It needs to be a negative 60 centimeters. Because our image is on the same side as our object, this is a virtual image, plus it's upright. So she sees it normally. So these guys both have to be in the same orientation. So this is going to be a virtual image, so its image distance is negative. So then when we solve for the focal length, we get that the focal length is 42.85 centimeters, which in order to find the power we need meters. So that's 0.4285 meters, and then our power is going to equal 1 over our focal length, so 1 over 0.4285, and that will give us 2.33 diopters. So we know that these are convex, and it's going to be 2.33 diopters for the power. Okay, same situation, except for this time it's with glasses. So the distance from where the image is going to be to her eye is going to be 60 centimeters. But the distance from that to the glasses, since the glasses are 2 centimeters in front of her eyes, that's only 58 centimeters. Okay, if I did that too fast, just rewind and listen to it again. Okay. The object, she still wants to be able to hold the book at the same spot. So the object is going to be 25 centimeters in front of her eye, which puts it 23 centimeters in front of the glasses, because it's the glasses that are making the image. All right? So 1 over f, we're going to use these distances here, the 58 centimeters and the 23 centimeters. So basically, we subtracted the distance the glasses were from the eye from our image and our object distance. is equal to 1 over, remember it's going to be negative 58 because it's a virtual image, plus 1 over 23. So we'll get a focal length of 38.1 centimeters. Okay, which is 0.381 meters. And so when we go to find the power, we're going to go 1 divided by 0.381, and we're going to get a power of 2.62 diopters. And that would be the glasses that she would need to get from the Dollar Tree. But the Dollar Tree doesn't have 2.62s. It does have 2.5s. So 2.5 is close. And so she would go get 2.5s. All right. So you do have some practice problems on this, and I'm here if you need help.